Hi, grade 9 students. Congratulations on finishing up Unit 3. Looked like people were doing very well on it. And moving into Unit 4. So, Unit 4 is all about linear relations. And linear implies lines, and relations, just short for relationships. So, we're going to be discussing the patterns that we see in mathematics and the relationships of two different sets of data. Okay, so, let's just dive right into 4.1. A landscape designer uses wooden boards as edging for the plots in an herb garden. So there's the first plot, an example. It's got four walls. The second one has one, two, three, four, five, six, 7 walls to separate the two plots, and then so on and so forth. So we want to talk about the relationship between the number of plots there are and the number of boards that we need to build each one of these little gardens. So the number of boards is related to the number of plots, and we've got to figure out how they're related. We can represent relationships using pictures, like we did up here. We can use table of values, and we can use equations. And sometimes we can use values to create equations, and we can use equations to create tables, and we can use one of these to create the other two. So there's a couple different ways to determine an equation or to figure out how we are going to make one sort of statement, one mathematical statement that will tell us the relationship between boards and plots, no matter how many plots we have. We've only got it up to 4 here, but what if we needed 40 plots? It'd be much easier for us to do a mathematical equation than it would, or expression, than it would be for us to draw this out 4, 5, 6, 7, all the way up to 40. So let's use the plots here, the picture, to create what's known as a table of values. And this can be very, very helpful in making that mathematic expression. So let's see what we got here. For the number of plots, okay, we've got plot 1, okay, we've got plot 2, we've got plot 3, and plot 4. We'll worry about the rest of these later. What is the pattern in the number of boards? Well, it might be easiest for us to fill this out first. Let's count the number of boards, and then we'll get to seeing what the pattern is. So we've got one plot, we've got 4 boards. Okay, if we move to 2 plots, we've got 1, 2, 3, 4, 5, 6, 7 boards. Remember, this board is shared, so we don't have to count it twice. For this one, 3 plots, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, remember, we didn't include duplicate boards here. So let me just count that again and make sure I didn't get it wrong. We need 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, because we need a board there. 5, 6, 7, need a board there. And then 8, 9, 10. All right, so I was trying to be careful there. We only need to count this board once and this board once, right? Because we don't have to have 2 boards back to back. So it helps to kind of look at where the overlaps are, just like we did in Unit 1, and make sure that you don't double count them. All right, let's go to the 4th plot. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so based on our picture, we've been able to fill out this table of values, and now we can figure out the pattern in the number of boards. So what's happening here? Well, nothing yet because we haven't started. But if we go from here to here, the pattern is we need plus 3 boards. When we go from here to here, it's plus 3 boards again. And then from here to here is plus 3 boards. So now what we can do is we can extrapolate our data, which means we can just continue it on. Even though we don't have a picture for this, we should be able to figure out, okay, what the next 2 are going to be. Because we're adding 3 every time, right? 4 to 7, that's 3, plus 3, plus 3. Well, plus another 3 is 16. And plus another 3 is 19, right? So really what's happening here is the number of boards is plus 3. So boards plus 3 is always going to give us this number right here. So we could use this chart if we needed to get 40 plots. We could use this chart and just continue from 6 all the way down to 40. But again, that's a lot of writing, and it's probably not very efficient. So what would be best for us is if we can create some sort of mathematical expression where we just plug in the numbers, and then it gives us the number of boards we need. So each garden needs 1 board for the left border and 3 additional boards for each plot. Okay, so it's the 3 additional boards for each plot that we're adding on every time. If you think about it, it's basically adding on the end piece. We need 1, 2, 3 for the end piece, 1, 2, 3 for the end piece, 1, 2, 3 for the end piece. So every time we do that, we add another 3 boards. So the number of boards equals 1 plus the number of plots times 3. All right? So as an equation, we usually start with the multiplication first. So our plots is P. Okay? So don't forget that. Plots equals P. Boards equals B. So let's use these variables in our equation and see if we can set something up. So let's start with this. Start with multiplication. So it's times 3. We're going to put the number out front. 3, okay, times the number of plots, that's P, okay, plus 1. And that's going to give us a mathematical equation or expression that we can use to figure out any one of these. So let's test this, okay? Let's test this and see if it works. Okay, let's test it with number 3, okay? So for 3 plots. Okay, if we know we have 3 plots, can we figure out the number of boards just using a mathematical equation? Okay, so that boards equals 3 times P plus 1. So the number of boards is going to equal 3 times the plot, which is 3, plus 1. 3 times 3 is 9, plus 1 is 10. It checks out. So let's check another one. Let's check out 5. So 5 plots. Okay, we've got number of boards equals 3 times P plus 1. So the number of boards equals 3 times the number of plots. In this case, it's going to be 5 plus 1. So B is going to equal 3 times 5 is 15 plus 1 is 16. Does that match our chart, our table? Yes, it does. So this checks out twice, which means that we've created an expression here that we can use to do as many boards as we want. So sorry, I accidentally shut my computer off there. So let's go and do that one that I said, what if we needed 40 plots and we didn't know how many boards? Okay, so let's just say we had a question like how many boards do we need for 40 plots? Because I don't want to draw a picture and have to go up to 40, and I don't want to make a table that goes down to 40. That's a lot of writing. It's a lot easier if I just use the expression we created. So our boards is going to be equal to 3P plus 1. Okay, so boards are going to be equal to 3 times our 40 plots that we want, plus 1 board. 3 times 40 is 120, plus 1. So our total is 121 boards. So I can just go to the store knowing that I need 121 boards, and I didn't have to do a whole bunch of drawing, and I didn't have to make a table that was really large. Okay. So this is just kind of the short version of the plots and boards. So we went 1, 2, 3, 4. We had a picture of 4, and we knew we needed 4 here, 7, 10, 13. And the way that you're typically gonna write this when you're trying to figure out what your expression is going to be is you are going to make little arrows that indicate it's going to be plus 3. And it has to be the same each time, otherwise you can't create an expression. Okay? So these have to be consistent. And then you also want to check over here what's happening with this side. And for this side, it's plus 1, plus 1, plus 1. And we can use this to create, okay, use this to create our expression. So the terms 3p plus 1 form an expression. Okay, you can tell the difference between an expression and an equation because an equation always has an equal sign. Okay? An expression just is a part of it that doesn't have an equal sign. So the equation for this is going to be b equals 3p plus 1. Okay, so let's write that down here just in the margin somewhere. Equations always have an equal sign. Okay, so that's how you can tell the difference between an equation and an expression. We verify the equation by substituting values of b and p from the table. So we checked it. We actually did that on the first page. We checked, does it work for 4 plots? Yes, it did. Does it work for 1 plot? Did it work for 3 plots? And we checked it. So an equation gives us a general pattern rule. And remember, that pattern was we needed 3 more boards for every plot we added, right? So that was the pattern. If there is a pattern, okay, we say that it generalizes the pattern. Okay, so the equation generalizes the pattern. And what that means in sort of plain English is, instead of us having to do each of those pictures or tables one by one, okay, by hand, we can make a general solution for any number of boards and plots. Okay, so even if the number of plots was like 1,500,000, we can use that equation because we know it generalizes the solution. Okay, so the whole point of this is we don't have to do it by hand, and we don't have to use a whole lot of space. Once we get the mathematical expression and then equation, we can solve these things without having to do much more work. So in the equation, determine the value of y when x equals 3. Okay, so if x equals 3 in all of these, all you do is substitute 3 for x in every single equation, and then let's figure it out. A lot of these you can kind of common sense your way through, but we really like you to show your math on these so that when you make a mistake, we can give you some feedback on where it went wrong. So in this case, y, we don't know what y is, but we do know what x is, so let's substitute it in. So 2x is multiplication, because they're touching, right? So 2, and then I'm going to sub the x in, which is 3. 2 times 3 is 6. On this one, y equals 3 times x, which is 3, plus 2. BEDMAS says we have to do multiplication first, so that's 9 plus 2 equals 11. This one, we've got y equals 5 minus x. X is 3. Okay, so it's just straight subtraction. 5 minus 3 is 2. So when we substitute a number in for a variable, we can usually solve for the other letter. And you should always end these with the full y equals or x equals or whatever it is that we're looking for. All right, here's a second example, a word problem. An airplane is cruising at a height of 10,000 meters. It descends to land. That means it goes down, right? This table shows the height of the plane every minute after it begins its descent. The height of the plane changes at a constant rate. Now, this is important because it needs to be a constant rate for us to have a pattern that we can work with here. So let's look at, as I recommended before, what's happening here. When we go from 10,000 to 9,700, what we're doing is we're going down 300. Okay, so are we going down 300 here? Yes, we are. So we've started to see a pattern here, which is good. If we're starting to see a pattern, we know we can make what's called a linear relation. Okay, the relationship being the minutes are related to the height of the plane, or the minutes of descent. So I can somehow relate a 0 to the 10,000. They're connected. The 1 is connected to the 9,700. The 2 is connected to the 9,400. And if I can do that, I can start making an expression. Okay, now what's happening on this side? I'm going plus 1, and consistently plus 1, and consistently plus 1 the whole way. So that is also a good sign. So let's write an expression for height in terms of time since the plane began its descent. All right? So what's happening? Our time is going up, okay, but our height is going down. So what we usually do is you relate the time to the height and sort of get a starting point. If nothing has happened, okay, it's our t, okay, plus, it's our height, okay, minus the amount of time times 300, negative 300. So this is the constant part. So what we're trying to figure out in all of these is what is the height. Okay, they're going to give us the time and they want us to find the height. So we're always going to be doing, in this one, our looking for an expression, and then an equation later. So I'll actually leave the equation part. So when you're building your expression, what you want to do is you want to start with the thing that you're going to work with, which is time, because we're always going to be trying to figure out height in this question or in these questions. So let's start with the time. All right. So we've got 10,000 is our starting point, and our time, okay, and our time is 0. So let's go 10,000 minus our time, okay, that's our variable, the t, okay? And that'll work for the first one, because 10,000 minus 0 is 10,000, which is what it should be. But we also have to relate this in. Now, this is normally connected to the t minutes part. Okay, so whatever's on this side for your pattern, it's almost always connected to the other side of the chart. So it's usually also multiplication. So what we need to do is 10,000 minus t times negative 300. And we need to write this in a nicer sort of math way. And you don't want to use the x for multiplication anymore. So what this becomes is 10,000 minus, and then you put the number here first, 300, because it's negative 300, right? Times t. Okay. And this actually should have been a positive, but yoink. Minus t100 times 3. I'm actually going to get rid of the x because that just confuses everything. So if we start with our 10,000 and then we subtract whatever the time is times 300, we're going to get the right answer. And the reason is for each unit of time, which is plus 1, plus 1, plus 1, right? For each unit of time, you lose another 300. So if you lose if you take 1 minute, you should lose 300 feet. So 1 minute, okay, so negative 1 times 300 equals 10,000 minus 300 equals 9,700. If we have 3 units of time, okay, we started with our original 10,000 minus 3 times 300, which is 900, so it's 10,000 minus 900 gives us 9,100 meters. So that's how these are all related, right? You always started with 10,000 because that was at 0. And then you have to subtract, okay, 300 feet for every minute, which leads to multiplication. So our expression becomes 1,000 minus 300t. That's an expression because I don't have an equal sign. Okay, well now let's just use that expression in an equation. What are we trying to figure out? We're trying to figure out the height. So h is going to equal 10,000 minus our 300t. And if we know either the h or the t, we can solve it. We can't solve it if we don't know what t is or we don't know what h is. If we know one of the two of these, we can solve this equation. The way we've written this, we're hoping they'll give us t because we're trying to find h. So what is the height of the plane after 15 minutes? The height, we don't know. That was the whole point of us making the equation. But we do know that it's going to be 10,000 feet minus 300 times the time. And in this case, the time is 15 minutes. So that's 10,000. The toughest part of these is writing the initial expression and equation. After you've written the expression and the equation, it comes pretty easily. So 300 times 15 is 40,500. We took care of the multiplication first, right? Bed mass, bed mass, bed mass, always bed mass. So we took care of the multiplication first, and then we do the subtraction, and what we're left with is 5,500 feet. Make sure you use your units. All right. How long after the beginning of, it should be of its descent, does the plane land? Okay, so now, instead of giving us the t, they're asking for the t. We got to find out how long, right? So how long? That's t. Does the plane land? Well, when a plane lands, the height should be 0, shouldn't it? So this time, they've given us the h, but they haven't given us the t. So we got to figure out for the t. But you can use the exact same equation, okay? So let's just write out the equation first. H equals 10,000, okay, minus 300t. Okay? But they didn't give us the t. They gave us the h. So let's just substitute in our h. It's 0 equals 10,000, 0 because the plane's on the ground, minus 300t. What's t? We don't know yet. We got to solve it. Whenever you're trying to solve an equation and you've got a variable, so a letter, and then another number, you have to get the variable on one side alone and the number on the other side. Okay, number or numbers. So in this case, I've got 300t over here. I need to get all of that over to the other side. Well, if I'm subtracting, okay, the way that I get rid of it is I need to add 300t to the other side. Okay, so it's going away from this side and it's coming onto this side. A different way to look at that, and I think I've represented it in a slightly different way in other units, so maybe I'll do that just in case you're used to seeing it that way. How do I turn this into a 0? I have to add 300t, right? Because negative 300t plus a positive 300t will equal 0. Whatever I do to one side of the equation, I have to do to the other side to keep it balanced. So if I add 300t on this side of the equal sign, I have to add it on the other side of the equal sign. So what are we left with? We're left with 0 plus 300t, so that's just positive 300t equals 10,000. Nothing changed there. And negative 300 plus, that just equals 0, right? That was the whole point of that. So I'm not going to write 10,000 minus 0. That's pointless. So now I'm left with 300t on one side and 10,000 on the other. Whenever you have a number multiplied by a variable equals another number, you have to get the t by itself, okay, or the letter by itself. The way that you get rid of a multiplication statement, okay, the way you get rid of a multiplication statement is doing the opposite of multiplication, which is division. So in order to get the t alone on this side, I have to divide this whole thing by 300. And when I divide by 300 on one side, I also have to divide by 300 on the other side. And here's what happens. 300 on the top and 300 on the bottom, that just cancels out to 1. And 1 times t is just t. So now I've got the t alone, which is what I want. But because I divided by 300 on this side, I also have to divide by 300 on this side. So now I have to go 10,000 divide by 300 equals 33.3 repeated. Okay? Because this is time, okay, I've got to think in terms of time. I could say it takes 33.3 repeated minutes to hit the ground. But what I'd actually rather do in this case is keep my fractions. So 10,000 divided by 300, okay, you can cross out 2 of those zeros right away because there's 2 zeros on the bottom, 2 zeros on the top. So what this is really 100 over 30. What's 100 over 30 if I simplify that? 100 over 3, not 100 over 30. What is 100 over 3 if I write that in a fraction form? Well, it turns out 3 fits into 133 times, and I'm left with a third. So these two numbers are both exactly the same. 33.3 repeated and 33 and a third repeated are the same. Okay, so it doesn't matter if you solved that going to decimals or if you solved it going to fractions. You get the same value. They look different, but they mean the same thing. But what does this mean in terms of time? Okay, the 33 minutes part is pretty obvious. It's what is a third of 60 minutes? Well, if we find out, okay, 33 minutes is the easy part. But what about 1/3 of a minute? Okay, what is 1/3 of a minute? Well, a minute equals 60 seconds, right? So, okay, 1/3, okay, times 60 seconds, and we'll just put it over, we'll just put it over 1, because 60 can also be represented as 60 over 1, right? Any number. Let's cross simplify here. We've got a 3 and a 60. We can divide both of those by 3, so 3 divided by 3 is 1. 60 divided by 3 is 20. So in the end, we've got 1 times 20 is 20, okay, and 1 times 1 is 1, which equals 20. 20 what? Well, we were dealing with seconds. I should write that here, seconds. So 20 seconds. Now, it's not necessarily wrong to say 33 minutes and a third of a minute, but it's better. Okay, so I'd say best answer. It takes 33 minutes and 20 seconds for the plane to land. Okay, so just answering in the spirit of the question, it gave me time. So instead of using a fraction for time, I tried to convert that fraction into, I knew the minutes, it was going to be 33. Okay, it was going to be 33. It was the 1/3 or the 0.3 repeating that I didn't really want to leave. I didn't want to say 0.3 repeating of a minute because I don't think anybody would know what you're talking about. So we figured out what's a third of a minute. A third of a minute is 20 seconds. So 33 minutes, 20 seconds for the plane to land. All right, here's example 3. We're calling a cab. There's a fixed cost of $3.60. What that means is just for getting in the car, you're going to pay $3.60, even though you haven't gone anywhere yet. But then there's something called a variable cost that on top of that $3.60, you're going to pay $1.50 for each kilometer that the car has to drive. So if we're going to write an expression, okay, let's look at the fixed cost because that's going to be the plus. Okay, so it's going to be something plus $3.60. Okay, we only have to pay that $3.60 once, right? So we're not going to have to multiply this by anything. We only have to pay that once. What we do have to pay more than once is $1.50 for every kilometer. Okay, so let's just represent $1.50, okay, as 1.5. Okay, and then the distance, let's maybe say that distance equals d. So d equals distance. Okay, so it's going to be 1.5. This is just a box because we don't know what's in there. 1.5, which means $1.50 per kilometer. So the kilometers, it's going to be per distance, plus $3.60 should give us our final answer. And we can just test that with some very simple math. Let's just pretend we only went 1 kilometer. Okay? Well, it costs us $3.60 just to get in the car, and because we only went 1 kilometer, it should be $3.60 plus $1.50. Okay? So when we start solving this, if we only go 1 kilometer, it should cost us, what is that, $5.10. We'll just kind of keep that in mind. So this is our expression. And we're going to use that expression to create an equation. Because once we have an equation, we can actually start substituting and solving. So what is the equation? Let's just call C equals total cost, okay? Because we need another variable. We've got a D for distance and we've got a C for cost. So our total cost, C equals the expression we made, 1.5 times the distance plus $3.60. Okay? So let's see if it works. All right. So this is an equation because it's got an equal sign. But you notice it also includes our expression. What is the fare for an 11-kilometer ride? Okay, well, if it's 11 kilometers, D equals 11. So we're going to have to substitute that in. Okay, so let's look at our equation and let's see what we know and what we don't know. C equals 1.5 times D plus $3.60. What do we know? We don't know C, we do know D. So let's sub D in. C equals 1.5 times 11 plus 3.6, or $3.60. All right, so multiplication first before addition. Always got to remember our bed mass. So it's going to be 1.5 times 11 is 16.5. Okay, so C equals 16.5 plus the original $3.60. So our total cost, now we can just add them together. Our total cost is going to be $20, okay, and 10 cents. The cost for the ride is $20.10. Now, remember I said that we would check, we kind of just made a simple equation or a simple substitution to see if it would work, and we said that if we only go 1 kilometer, okay, if we only go 1 kilometer, it was going to cost us, what was it going to cost us? It was going to cost us $5.10. So let's just check. For 1 kilometer, okay, D is going to equal to 1, right? So C equals 1.5 times 1 plus 360. Okay, so C equals 1.5 times 1 is just 1.5 plus 360. C equals $5.10. So it checked out for us on the 1 kilometer. I always like to test with something easy, right? Instead of saying, well, let's test it for 53 kilometers, let's test it for 1 kilometer. Okay, so tested it for 1 kilometer. It ended up being what I thought it was going to be. Okay, and then said $20.10 for 11 kilometers. Now, you can always check these by going in reverse. Okay, so if you want to check them, let's start with the $20.10 and see if we get the same value for D. So if I'm testing, C equals 1.5D plus 360 or 3.6. Okay, let's start with the cost. Let's go $20.10 is equal to 1.5D plus 3.6. And I shouldn't say equals, I should say, does this equal? Because we're testing it, right? Okay, so what do we need to do? We need to get the 1.5D by itself on one side. Well, it's already positive over here, so why don't I just keep it there? So if I want to get this number on the other side so that the 1.5D can be alone, it's a positive 3.6, so let's subtract 3.6 from both sides, okay? So now what have we got here? Okay, so we've got 20.1 minus 3.6, which leaves us with 16.5. Does that equal, question mark, 1.5D? Because we got rid of it here, because that equals 0, right? 16.5 equals 1.5D. Now, in order to get the 1.5D, I'm just going to get rid of this little line here so you don't think I'm dividing. Okay, so now how am I going to turn 1.5D into just D? Well, 1.5 times D, that's multiplication. So we've got to do the opposite, which is division. So if we divide by 1.5, we have to do it to the other side as well. Okay? So 1.5D divided by 1.5, the 1.5's cancel out and you're just left with the D. 16.5 divided by 1.5 equals 11. So 11, okay, equals D. Now, is the distance that we started with equal to 11 kilometers? Yes. So it checks out. Okay, remember up here we started with 11 kilometers and we had to find the dollar amount. And we weren't sure if we were right, we were pretty sure, but we wanted to check it. So we went down here and said, well, I'll do it in reverse. Okay, so I'll say, this time I'll say I'm starting with the C instead of the D. I'm going to start with $20.10 and I'm going to try and figure out if this equation works when I run it backwards. So we solved for D and we found that distance equals 11 kilometers, which is what we started out with here, so we checked it, and it works fine. Always good to check your work. I'll use linear relations for save it for a different video. So that should take you through the assignment for 4.1. Maybe it wouldn't hurt to put a couple of little reminders here, when solving for a variable. One, get variable on one side alone. 2, divide by the number in front. There are special names for these, but we'll get to them later. Divide by the number in front of the variable. Okay? So that gets you the final answer, actually. So get the variable on one side alone. So that was what we did. That's what we did here. And then we divide by the number in front of the variable. So that's what we did here. And then, write your answer. And that should work well for you. If you have any questions or if it needs to be explained in a different way, let me know. Send us an email. Thank you.